Hi everyone, my name is Jake at TerraSmart, and today I will be giving you a tutorial of how to use SIFT. The first thing that you'll want to do is you'll drag and drop a KMZ file directly onto the map. It will automatically parse the polygons for you, but all you'll need to do is define them as either boundary zones, denoted by the color red, so areas in which we want modules to be populated, or exclusion zones, denoted by the color yellow, areas in which we don't want modules to be populated. So as you'll notice, on this site I already have a previously uploaded project. And around these three parcels, I have a 15-meter offset, as well as these internal exclusions, I have a 5-meter offset off of those. So we're good to go on our map, and the next thing that we need to do is start to define our product. So within the Products tab, we can now define our module, inverter, and racking. So if we click on the Module tab, click on the Import button, this is where you would drag and drop a pan file into this box, click Import, and all those module specifications will be uploaded into this tab. You can name that file, save it, and access it for any future jobs that you run in SIFT. We also have a small generic database of both mono and bifacial modules that you can select from if you'd like in the search bar. For instance, on this tutorial, I'm going to run it with a generic 535 watt bifacial module. So let's move on to the Inverter tab. We can also click on the Import button. This is where you would drag and drop an O&D file into this box, click Import, and all those inverter specifications will be automatically uploaded into this tab. Again, you can name it, save it, access it for any future runs. Also, again, we do have a small generic list of inverters that you can select from in the search bar. For this project, I'm just going to use a generic 1 megawatt inverter. Let's move on to racking. Notice that we have 3 rack types available: single axis tracker, ground fixed tilt, and east-west fixed. For this project, we're just going to stick with a single axis tracker. Once you define your number of modules per string, you can either input the rack dimensions automatically or manually. So if we click on manual, you can open up this table. Notice we have 3 nondescript rack sizes, A, B, and C. You can turn those on and off however you want them populated within your boundary. All you have to do is input the X and Y dimensions as well as the module counts for these racks. If you want a little bit of help from SIFT, you can click on Auto. What that will do, it will take those module dimensions from the module that you input in the Module tab. It'll apply those against several inputs in terms of modules height, orientation, rack size. You can open up this table. It's the same table as manual, but notice it's read only, and this will show you exactly what racks will be populated within your boundary. So if we close that out, notice at the bottom we also have a grade limit. That's important if we want to use the topography function. So this rack has a 10% grade limit, and then we round it out with a couple inputs in terms of the bifaciality and bifacial gain within the performance model, as well as for a single axis tracker backtracking. So from that point, we've defined our module, inverter, and racking, and we can move on to the Performance tab. Within Performance, let's go ahead and open up the Weather tab. So when you open this tab, notice that there's a pin on the center of the site. This is important because it's taking the correct latitude, longitude, elevation, and time zone and applying that weather data properly to this site. Similar to the Module and Inverter tab, you can click this Import button to where you can drag and drop a standard format CSV weather file into this box. Click Import, and all that data will automatically be imported into SIFT. Again, you can name it, save it, and access it for any future projects that you run in SIFT. If you don't have your own weather file, no problem. Within SIFT, you have the ability to choose from NSRDB or NASA Power. So for this project, we'll stick with NSRDB. Within the Performance tab, you'll notice that we have a list of performance loss inputs that mimic those of PV-SIST. And this is important because once you get to the end of the process in SIFT and you find a winning configuration, you can quickly and easily verify that the SIFT performance model is aligned with the PV-SIST performance model. And one thing to note in here is that we do have the ability to input monthly values for both soiling and albedo. So once you define all of your performance inputs, you can now move on to the Finance tab. Within the Finance tab, you'll notice that we have 2 options, LCOE or IRR. So we'll stick with IRR for this project. Once you define your analysis period and discount rate, notice that we have 5 categories of financial inputs for you to define, those being install costs, operating costs, revenue and incentives, debt, and tax and depreciation. So once you run these iterations, not only will you get layout and configuration and a performance model, but you'll also get all of that tied back to the internal rate of return for this project, and we can now move on to the Site tab. Next, we'll move on to Site. If we click on the Layout tab, under the word Limits, we have POI limit, or Point of Interconnect limit. If we toggle this on, this allows us to cap the AC generation on the site if the grid can only accept up to a certain amount of power at this location. We also have set inverter quantity, which allows us to cap the AC capacity on the site by multiplying the inverter quantity by the inverter rating defined earlier in the Products tab. Also, under the word Options, these are all functions that allow us to consume a certain amount of space within the boundary on our map, which allows us to create a more or less conservative layout based on our preference. And we also have the ability to choose a layout coordinate system, which will georeference any CAD file that we download at the end of this process once we find a winning configuration in SIFT. And the last thing that I'll show you on the map here, as you can see, I have already brought in riparian, wetland, and FEMA data by clicking on this icon and selecting these toggles here. And I also downloaded a 10-meter data set from USGS for topography, which brings in this elevation layer, and based on that, we can create a max slope analysis layer, a north-south slope analysis layer for single-axis trackers, and an east-west slope analysis layer for ground fixed tilt systems. And now that everything is defined, we just have to move into this config tab and we'll be ready to go. So let's go ahead and navigate down to the config tab. And this is really where the power of SIFT lies. So what we'll be asking SIFT to analyze today is a range of GCRs from 0.3 to 0.7 at a 0.02 step, giving us 21 total GCRs. It also has the ability to analyze a range of pitches if you're more comfortable with that variable, but for this tutorial we'll stick with GCR. And we'll also be asking SIFT to analyze a range of DC-AC ratios from about 1.1 to 1.5 based on a min and max strings per inverter at a 2-step, giving us 15 total DC-AC ratios. So I'll go ahead and hit run. And if we open up this config tab again, it's taking all this information that we defined, packaging it up, sending it to the cloud, and it's taking these 21 total GCRs against these 15 total DC-AC ratios, and it will be giving us 315 layouts, 315 performance models, and 315 internal rate of return calculations for the life of this project. You can expect to get results in a matter of 15 to 60 seconds based on the size of your site. SIFT is certainly built for speed, and as you can see, our results popped up. So let's take a look. So now that we have our results, notice that each one of these rows represents one of these 315 iterations that we asked SIFT to create for us. So if we'd like to dive deeper into any of this raw data, all you have to do is click on any of these headers for the columns, and that will sort that data from top to bottom as you see fit. Also notice that on the right side of the screen, SIFT took those 315 iterations and plotted them on a colorful heat map, and this allows us to visually understand where the value lies in terms of IRR for this project based on those ranges of GCRs and DC-AC ratios that we defined earlier in the config tab. So since we're after the highest IRR and we have a nice parabola on our heat map, let's navigate to the IRR column and sort from top to bottom. And we'll see that SIFT is telling us that the highest achievable IRR is 9.871% with a configuration of a GCR of about 0.36 and a DC-AC ratio of about 1.30. Also note that for this specific configuration, the maximum DC capacity is about 13 megawatts, but SIFT can accommodate up to 1 gigawatt. So let's go ahead and double click this iteration. A new tab is updated. Notice that the layout is automatically plotted on the map for us. And we can go ahead and open up this north-south slope analysis layer that was created based on the USGS topo data we imported earlier. And notice that the layout has removed racks that are outside of a 10% grade limit that is denoted by these gray areas on the map. So just another cool function within SIFT to make sure that the layout we're getting is considering the topography on the site. Also note that this isn't going to be a perfect layout, but you can certainly georeference the layout. Click on this CAD button that will download a DXF file, and we can take that DXF, plug it into AutoCAD, start to move those racks around and update that layout however you see fit. You can also download a CSV file for this specific configuration that will give you a summary of all the products that we used, as well as the loss output scheme. And this is important, again, when we want to quickly and easily verify that the SIFT performance model is aligned with the PV-SIST performance model. We'll also get 8760 data for both the DC and AC side of the project, as well as a complete internal rate of return calculation for the life of this project across this iteration. So from this point, we can navigate back to the raw data and we can sort however we see fit. We can open up different iterations and start to compare and contrast the data from tab to tab. We can also start to compare different modules, inverters, and racking. And we can also expand or reduce those GCR and DC-AC ratio ranges as we see fit. So from this point, SIFT gives us a really quick and easy way to understand which configuration will give us the best value for this site and these products. And the last thing that I'll leave you with is on the bottom left-hand side of the screen, we have a Send Bug Report button. We do pride ourselves on customer service, so if you ever run into any issues or errors or problems, click on this button, type in the description, hit send. Our entire team will be pinged and we will get back to you with the solution as soon as possible. And that's it for the tutorial today. Thank you so much for joining me and we hope to see you soon.